In this video, we're going to take what we just learned about finding volume using the disk method and apply it to using the washer method. Now we want to take a look at how to find the volume when we have the same type of figure we had before. So if you'll recall, we called this W and we called this distance R. And now what we have is we have a smaller radius, which we're going to call little r. So we can see that if we're going to take this figure that is now separated from the x-axis and we're going to rotate it about the x-axis, we would end up with a hole in our figure. The radius of the hole would be that little r value, and of course the radius of the larger disk would be the big R value, and we would still have W here. So now if this was just a regular washer, like in this case, we would find the volume by taking pi r squared W, whoops, sorry about that, pi r squared W, and then we would subtract pi r squared W with the little r. So I would be taking the first value, which would give me all of this including the whole, and then we would simply subtract out the whole. Now of course that's if we have a volume that has a constant width, constant radius. So obviously in calculus that's not the case. So what we're going to do instead is we're going to first consolidate this a little bit, because obviously I could take r squared minus little r squared. And so turning this into a calculus equation for varying radius means I have pi, and then I'm going to integrate big R squared minus little r squared dx. So just as I did before when I made some changes, but I want you to notice that I am squaring big R and I am squaring little r. So big R squared minus little r squared is not the same thing as big R minus little r squared. Those are not equal. We want to find the big volume and subtract the little volume. So this is not what we're doing in this video. So let's take a look at our first example to find the volume of the solid formed by revolving the region bound by y equals 6, y equals 3, x equals 2, and x equals 5 about the x-axis. So again, because it's about the x-axis, this is our first one like this, the first thing we should do is always to draw the figure. So again, I've used Desmos to draw the lines for me, but this is the region that we're talking about, is we're taking that square and we're going to revolve it around the x-axis. So it's always helpful to think about what your figure would look like. So when you're revolving around the x-axis, the easiest way to draw that figure is to reflect the figure across the x-axis, and then I'm simply going to connect the dots. So that gives me the basic idea of what my figure is going to look like, and you can add in the dotted lines as well. But it's essentially just a washer. That's what we're dealing with, is just a washer. So the next thing I need to do now is think about the formula. And the formula says I'm going to take pi times the integral from a to b of big R squared minus little r squared dx, keeping in mind that big R squared was the outer part of my figure and little r squared was the inner part of my figure. So again, what do I not know? Well, right now I don't know AB, and A and B are the limits of integration. Because I'm going about the x-axis, the limits of integration are given in my question. So now I have the volume equals the integral, I'm sorry, I forgot pi. Pi times the integral from 2 to 5, and now I have to determine what is big R squared and what is little r squared. So keeping in mind that this is my axis of revolution at the x-axis, or y equals 0, I'm going to take big R to be this distance, and that distance is just the function y equals 6. And then little r is going to be this distance, and little r is the function y equals 3. So minus 3 squared. And again, this is with respect to x. So that's going to give me pi times the integral from 2 to 5 of 36 minus 9 dx. I can continue to simplify. I have pi times the integral from 2 to 5 of 27 dx. Now I'm actually going to integrate, which tells me that I have pi, and then this is just 27x from 2 to 5. So my volume is pi times 27 times 5 minus 27 times 2, which gives me pi times 81, or 81 pi. So my exact result is 81 pi. Keep in mind that I might want the approximate solution, so keep in mind as to what they're asking you for in the question. But again, this would be 254.46 approximately. And again, this is a volume, so units cubed if they need it to be labeled. Now, I wanted to do the same question on the same slide because I already have my silly little picture. And this time I want to revolve around the line y equals 2. So we just want to see how this is going to change everything. So I still have the same figure to begin with, right? But now I'm revolving around the line y equals 2, which is this line right here. So we can see that my figure is going to be a little bit different. I'm going to end up with a smaller washer, but it's still going to be a washer. Now, how is that going to look mathematically? Well, mathematically, I'm still going to have pi, and I'm still going to have from 2 to 5 because it's the same limits of integration. But now, big R needs to be this distance. So how do I find this distance? Well, luckily, we already know that idea or that concept is to take the function, which our function here is y equals 6, and subtract. So this is kind of like our f of x, and this line right here is kind of like my g of x. So that's what I'm going to do, is I'm going to take 6 minus 2 quantity squared for the big R, and then for my little r, I'm going to take the function, which is 3, minus, again, g of x, which is 2, quantity squared, and then dx. So same idea, but notice all I've done is now I've subtracted. So I have pi, and then the integral from 2 to 5 of 6 minus 2, or 4 squared, and then 3 minus 2, which is 1 squared, which gives me pi times the integral from 2 to 5 of 4 squared is 16 minus 1, so I have 15, and I forgot dx right here. So I've got 15 dx. Now I'm going to obviously integrate. So I have pi, and then I have 15x, and then 2 to 5. So again, I'm going to have pi, and then 15 times 5 minus 15 times 2, which gives me 45 pi, or approximately 141.372 cubic units. So we can see the difference there in just moving the line is where I have to do some subtraction. So it can get a little bit tricky knowing where to square and where to subtract. So that's why we're going to do a lot of examples. Let's take a look at another example. We want to find the volume of the solid formed by revolving the region bound by y equals x squared, y equals radical x, about the x-axis. So again, first thing we need to do is you need to graph those two functions so that you know what you're dealing with. So the region that we're talking about is this region right here. And again, what I want to do is I want to think about what would that look like if I reflected it across the x-axis, and then simply make a solid. So it's going to be very, very wide at the top, and obviously it's going to be kind of like a bowl. So a bowl with this region right here cut out. So again, how am I going to do this? Well, I need to know my limits of integration, and it's not given to me, and obviously I can kind of cheat and look at my picture, but you should know how to mathematically find your limits. So in my last question it was essentially given to me, but in this question I'm going to set my first function of x squared equal to my second function of radical x. So how am I going to solve this? Well, if I square each side I get x to the fourth, x to the fourth equals x. I can put them both on the same side, which would give me x cubed minus 1. And essentially what I'm going to be looking at here is x equals 0, and then setting this equal to 0 would give me 1. So those are my limits of integration. And again, I can check that by looking at the picture. From here, I'm going to now integrate. So I have to set up the formula and integrate. So my limits are 0 to 1, so to find the volume, I'm going to take pi, and then from 0 to 1, and remember big R minus little r. Now I'm revolving around the y-axis, so I don't need to worry about subtracting anything from big R or little r, but which one is which is the big question. So I can see on my picture that the parabola is y equals x squared, and this guy, oops, I meant to change color there, I apologize. This guy is the function y equals radical x. So which function is the top function? Y equals radical x. So that has to be big R. So that's going to be radical x squared. The little function, or little r, is x squared, and again, squared, and then of course all of that with respect to x. So from here it's now just doing the math. So we've done the hard part, I feel like. So now I have the volume equals pi, and then from 0 to 1. If I square the square root of x, I just get x. And if I square x squared, I get x to the fourth. And now I'm going to integrate. So if I integrate x, I get x squared over 2. If I integrate x to the fourth, I get x to the fifth over 5. Again, from 0 to 1. So my volume is pi times, and then 1/2 minus 1/5, and then essentially minus 0 minus 0, which gives me an exact result of 3/10 pi and an approximate result of 0.943 cubic units. Here's another example, and I really like this one because it makes sure that you are paying attention to what the appropriate function or formula is to use. So again, here's the question. I'm trying to find the volume of the solid formed by revolving the region bound by y equals 0, y equals the square root of x minus 1, x equals 0, and y equals 1 about the x-axis. And again, I can use Desmos to help me visualize what's going on. And so essentially I'm looking at this region right here. Now if I revolve that around the x-axis, it's going to look something like this, obviously with a curved bottom instead. But that's essentially what it's going to look like. So I have a sort of a hole here, but if you'll notice, this region from here to here is actually solid. And so that's why I like this question, is because I actually have to split this into two different parts. So the first thing I'm going to do is note that this function starts with the whole, or starts looking more like a washer at the point x equals 1. And I could find that, of course, by setting this guy and finding the vertex of that part of the figure. Instead, though, let's just focus on finding the limit. Now again, I can look at my picture and know that the last part of my figure goes to x equals 2, but you should be working to find that yourself. So again, radical x minus 1 equal to 1, square each side, and find that x equals 2. So again, for me to find the volume, I'm going to have to find the volume of this part of my figure, which I'll color in yellow, and then the volume of, oops, I tried to change color, but it didn't work. The volume of this part of my figure, which I'll do in green. So let's start with the yellow. The yellow is a disk, and when we did a disk, we said that was pi, and again, this would be from 0 to 1, because that's where the disk would end, from 0 to 1 of, and I don't need to do any subtraction or anything here, I'm just looking at big R. So what's big R? Big R is this line, which is y equals 1. So that makes it really easy. 1 squared dx. I'm going to add to that this area, which of course is not a disk, it is a washer. So I have to use the washer method. So pi, and this one is from 1 to 2, so from 1 to 2, and the big R would still be 1 squared. The little r would be this function that makes the part of the whole, which is radical x minus 1 squared, and then dx. So let's get cracking here. Again, from 0 to 1 of 1 squared, which is just 1 dx, and then this is from 1 to 2, and then simplifying what I have in here, obviously 1 squared is just 1, and the square root of x minus 1 squared is x minus 1, so I have 1 minus x minus 1, which gives me x plus 2, I'm sorry, negative x plus 2, or 2 minus x. I guess it doesn't really matter how you do that. 2 minus x. So, and again, that's dx. And so continuing, I'll have pi, and I'm just going to take the pi outside for the entire thing, so I'm going to bring both of those pi's to the outside. If I integrate 1 dx, I just get x, and that's from 0 to 1. And then if I integrate 2 minus x, I'm going to end up with 2x minus x squared over 2, and that's from 1 to 2. And again, the whole thing is going to be multiplied by pi. So continuing my work, I'm going to have 1 minus 0, and then for my second one, using 2, so 2 times 2 is 4, minus 2 squared, which is 4 over 2, or 2, and then plugging in 1, I get 2 times 1 minus 1/2. And again, everything's going to be multiplied by pi. So I'm going to end up, and I'm going to skip showing all of those intermediate steps in between because it's just algebra, so I'm assuming you can simplify very easily to find that the volume is 1.5 pi. And then again, if I need that as an approximate solution, 4.712 is my solution. We'll take a look at one last example, and again, this one we are going to revolve about the y-axis, and so that's obviously going to mean that we're going to need to integrate with respect to y. So the first thing I should do is draw the picture, and again, feel free to use technology to help you. And I can see that the region that I'm talking about here is this region right here that I've now outlined in black, and if I want to revolve that about the y-axis, it's going to look something like this. And again, a 3D figure. So we did an example like this before with respect to x instead of respect to y, and we found that there were actually two different regions. And so I have a region here that is clearly a disk, whereas this region up here is clearly a washer. So I'm going to separate it into two parts, but again, I need to know my limits of integration, and my limits of integration should be with respect to y. So obviously 0 is going to be the lower limit of integration. For my first figure, that goes from 0 to 1, and for my second, it goes from 1 to 2. And again, you should be able to show that work for where you found the 2. The 1 can be found just using the fact that it is a parabola, and that is where the vertex would be, is at 1. But in order to find the 2, you would need to have the function of x equals 1, which is the purple line on my picture right here. I want to know where does that meet the red line. So I need to set those two equal to one another. So x equals 1. Notice this function, my first function, is not in respect to x. It's a y equals equation, not an x equals. So first I would subtract 1 from each side, and then I would take the square root. So this is my new function. This is the one you're going to see me use, and I'm going to set radical y minus 1 equal to 1, because now this is in terms of x, and this was already in terms of x. So if I square each side and then add 1 to each side, that's where I find that y equals 2 value. So now let's get started on actually doing the integration. To find the volume, again, I have two separate parts. So the first part is the disk, and that is going to go from 0 to 1. And remember, I'm looking for just the big R radius. And the big R radius in this case would be that purple line, which is the function x equals 1. So that's what I have here, is 1 squared dy. The other function, which I have colored in blue, will go from 1 to 2. Oops, don't forget pi. We'll go from 1 to 2. And again, this one I'm going to use big R, little r. So from here, big R is still the function x equals 1. Little r is this function, which of course is the one that I have manipulated into an x equals form here, and that's the form I'm going to use. So I have 1 squared minus the square root of y minus 1 squared dy. And now I'm just going to do all of my simplification. So pi, again from 0 to 1, of 1 squared, which is 1 dy, and then pi from 1 to 2, integrating from 1 to 2, of 1 squared obviously is 1, and then y minus 1, the square root of that squared is y minus 1, and so that leaves me with 2 minus y dy. Continuing, I will now integrate. I have pi, and then 1 integrated is just y, and that's again from 0 to 1. And then I have pi, and again, I could have taken the pi out of both as I did in my last example like this. It really doesn't matter. 2, if I integrate that, I get 2y. If I integrate y, I get y squared over 2, again from 1 to 2. So now I'm going to start plugging in the values. So I have pi, and then this is 1 minus 0. And then I have pi, and I have 2 times y, which is 4, minus 2 squared divided by 2, so 4 divided by 2 is 2, minus 2 times 1, which is 2, minus 1 squared over 2. And so again, I now have pi times 1, which I'm just going to write as pi, plus pi times, I'll go ahead and put the 1 in front just to keep track. Here I have 4 minus 2, which of course is 2, and then 2 minus 1/2, which is 1.5, and so I'm taking 2 minus 1.5, which gives me 0.5 or 1/2. So if I add those together, I end up with 3/2 pi as an exact result, or 4.712 as a rounded result. And again, that would be cubic units. So I realize that we've already spent quite a bit of time together in section 7.2, but there is one more part of this section that we need to talk about, which is finding the volume of a solid with known cross sections.